Okay, so welcome to class 23. So I'm not going to record class 22, which was on my research, but I hope you got some interesting insights about how statistical mechanics is used in the modern research context. So in today's class, we are going to do something called the H theorem. And to do that, we need to discuss the principle of detailed balance, which essentially is the condition for equilibrium, microscopic equilibrium. So how do we know whether a system um, is in equilibrium? So basically, microscopic currents between different states has to be zero. Uh, so so that's so macroscopically actually what you do. I mean, the example that I had given of equilibrium, the beginning of the class was so what is equilibrium? That there should be no charge current, there should be no density current, there should be no momentum current, there should be no energy current, and so on and so forth. So that example where suppose you take a block of metal, and on one side you maintain by a suitable heat path a temperature of T2, and on the other side you maintain a temperature of T1, and then over time, by Fourier's law, the temperature there will be a uniform temperature gradient, which means that the temperature from one end, the end where the temperature is higher, uh, suppose that's T2, the temperature will fall linearly with x being the direction along the the metal rod. So as you go from one end to the other end, and that's x increasing, so temperature will fall linearly. And at some point of time, the temperature profile is going to be uniform as a function of time. It's not going to change anymore. And the question I had asked is whether that's equilibrium. Uh, Properties of the system are not changing. The answer is no, because on two sides you have two different temperatures, and moreover, there is an energy current. There is a heat flux which is going from one end of the polymer, and sorry, the rod to the other. Uh, so that's not a condition of equilibrium, that's a condition of steady state. Now, microscopically as well, there is a condition that there should be no current between two energy levels, say, or microstates. And that's the principle of detailed balance. Uh, and it comes from something called, very generic, called the master equations. And the master equation and the principle of detailed balance will tell you the condition of equilibrium. And using the master's equation, we shall show that if an isolated system, and I emphasize the word isolated system, is left to itself, it will reach equilibrium under the condition that there will be no microscopic current inside the system. And if as a system is evolving towards equilibrium, one can show that there's a certain quantity called H. H is not the Hamiltonian. H is a certain quantity which shall define, and we call it H because Boltzmann called it H for whatever reason. We should show that the H actually keeps on decreasing, and the rate of change of H becomes equal to zero only once the system reaches equilibrium. Now, this H continuously decreasing till a system reaches equilibrium, an isolated system reaches equilibrium. This is very analogous to entropy increasing, and equilibrium will be reached once entropy is maximized. In fact, one can show the, I mean, though one defined things in terms of H, it was later shown that basically H is nothing but negative of the entropy. So basically, I mean, entropy was defined as later as negative of H, in fact. But historically, they showed that H decreases. This is equivalent to say that entropy increases in any natural process till an isolated system reaches equilibrium. So these are the points we are going to cover in today's class. This is the big picture. So how a system reaches equilibrium, what is the condition of equilibrium? The question is also, if a system, isolated system left to itself, if it is in non-equilibrium, will it always reach equilibrium? I mean, why should we believe that a system will reach equilibrium, and so on and so forth? So these are the questions. Which could be asked, because in the past we assumed equilibrium and developed microcanonical ensemble and so on and so forth, assuming equilibrium. But why will a system reach equilibrium? Should we believe that? These are the kind of questions which I'm going to discuss in today's class. Going into further detail, so this Boltzmann-S theorem is in the Rife Appendix A12, and later you shall see that topics of master equation are in Rife chapter 15.1, and for the canonical case, this is an isolated system, and master equation and principle of detailed balance are in chapter 15.1 and 15.2, right? So the question we are asking is, are the conditions of equilibrium isolated system? It's to be highlighted. Typically, when we started off discussing microcanonical ensemble, we assumed the system has reached equilibrium and started framing principles, postulates of how the different microstates will behave. All microstates will be accessed with equal probability, and so on and so forth. So where did this come from? So we also thought that there should be no current in the system. Thermodynamic currents is what we had in mind, and the system is not going to evolve as a function of time. It's an isolated system left in equilibrium will remain in equilibrium. All microstates will be equally probable, and the properties of the system are not going to evolve with time because it's in equilibrium. It's isolated, right? So all macroscopic properties were time independent. Uh, there was no net current in the system, and then we postulated that all microstates are equally probable, and that there is no bias in the equations of motion to choose preferable microstates in the laws of mechanics. So all microstates, all ways of distributing a system in different microstates, there is no bias, and it has to be in equal probability. But that's for an isolated system. But for an isolated system, which is the canonical system, basically a system in contact with a heat reservoir, we know that all microstates are not equally probable. So higher energy microstates are less probable to be accessed, any microstate at higher energy, and that is proportional to e to the minus beta h, the energy by the partition function, right? So that's a system in equilibrium. But non-isolated systems, you could also have non-equilibrium or driven systems, where you drive it to maintain a uniform current or so on and so forth. So that's also a non-isolated system. I mean, not all systems are going to, okay, an non-isolated system can reach equilibrium in contact with a heat path, but if you're constantly driving it, you're putting energy at one end of the system and taking out energy at some other end, then there will be a current, and that could be, I mean, not only energy, but you could put in mass constantly at one end of the system, and there will be a drift of mass from one end to the other, and those will be non-equilibrium or driven systems. But we are not going to discuss that. But just for the sake of completeness, I just mentioned that. Okay, so the question is, what? So suppose you have an isolated system, You have an isolated system, and if all microstates were not equally probable in an isolated system, what can we say about that system? So it's isolated. This all microstates are not equally probable, which means it's in non-equilibrium. And the question is, how are these probabilities going to evolve? Can we say something at all? So to start discussing it, what we start with is a very general statement, right? So suppose P of R probably at a time t is the probability of finding a system in state microstate uh, R at a certain time t. Now, suppose there can be tons of different microstates, different ways of arranging their momenta and position, right? Uh, Now, if you had an ensemble of system and it's not in equilibrium, all microstates are not equal. But anyway, the system has to be somewhere or the, I mean, it has to be defined. It's in a box, you have n particles, there's a certain amount of energy, right? It's isolated, but energy is not uniformly distributed. Some parts of the gas molecules are suppose moving at higher velocities, or some part of the box has more number of particles. But the sum of all probabilities for all microstates, even if they are not equally probable, has to be equal to 1, right? And we can also in general define something called the transitional probability, which is suppose it was the system was in a state P, a microstate uh, P, um, yeah, uh, yeah, and the probability. So probability of the system going from state P to state S. Now, if we think about our system quantum mechanically, because most systems are, I mean, all systems are quantum mechanical, you could say that the system is defined by some Hamiltonian H0, and the system is in one of the eigenstates. So there are many eigenstates, there are many quantum states of the system, and the system is in a particular eigenstate of Hamiltonian H0. And in that case, the transitional probability will be the probability that the system is going to go from state P to state S, right? So that's WPS. It's the transitional probability, the probability that the system is going to go from one quantum state P to another quantum state S. Now, if a system is already in an eigenstate, it doesn't have any reason to evolve to a different quantum state S, unless there is a small perturbation, which we shall call H1. Okay, so the total Hamiltonian is made up of H0, and H0 defines the quantum states, and there is another small interaction, an extra term, perturbation, H1, and that is what is driving the system to go from one quantum state to the other. So and as it goes around different quantum states, or if you like microstates itself, which classically will be due to collisions, right? So p square by 2m is this h0 if you want to think classically, and h1 is the effect of collisions, microscopic transitions from one because the particles are also moving, and there can be collisions, so it can go from one microstate to the other. So that's the way to think classically. And then you can say that del PR. So PR, if you want to say, if you want to think classically, it's a microstate with positions and momentums. If you want to think quantum mechanically, it's in one eigenstate PR, and it's going from one to the other. And then you ask in most general, you can write down this so-called the master equation, which describes the rate of change of PR. So how much this probability of the probability of a system being in a state R, how does it change as a function of time? So ddt, rate of change with time of the probability of the system being in a state R, is proportional to now consider that you have an so basically you have an ensemble of systems. So you have an ensemble of systems. So each system has many microstates, right? But now you are saying that you have parallel many systems, and each of those systems are in any of those microstates. And basically what you are thinking, the broad picture is some of those systems are in state, say, S, and they are relaxing with a transition probability of Ws going to R. So this is the transitional probability. So if they are in state S, a certain number of particles are systems are in state S, then this is the probability of being in state S. And if a certain number, so into the total number of systems is the total number of the total is the number of systems which are in state S. So if you want to think if probability is an abstract concept, then you can also convert it into the number of systems which are in state S into the transition probability that the system S is going from S to R. So that is going to lead to an increase of the probability of the system being in state R, or if you like, if a certain number of systems are going from S to R, the number of states which are in R is going to increase, right? Now, S could be any state. So there's a sum of the many different states. The different systems are in different states, and some of them are changing from state S, and S could be 1, 2, 3, 4, anything except R, and a certain number of them are going from S to R, and that is leading to an increase in the probability of P of R, or you could say that it's going to increase the number of states that are in R. But also some of the states which are in R, so suppose there is a certain number, N3 number of systems which are in state R. Some of them are also going away to state S, right? And so if you just multiply by the total number of systems that are in state 1, 2, 3, 4, 5, 6, the total number of various states, that is possible. Or analogously, if you divide by the total number of states, then you get the probability that okay, only a certain fraction of systems are in state R, a certain number of systems are in state R1, a different number of systems are in state S, and so on and so forth. And from state R, some of the systems are going away to the different states S. So there's a sum over states. It can go to next state, the next after that, and so on and so forth. I mean, next is not in position, but suppose you just arrange them, like call them 1, 2, 3, 4, 5. So, right, and that will depend upon the transition probability of going from R to S. And a statement of this form right? So how many systems are entering state S, which is from different other states? Sorry, how many systems are entering state R from S different states, and how many systems from R are going away to state S? So such an equation is called the master's equation. It's a very generic equation. You're just saying the number of particles coming in equal to number of particles going out is equal to the change in the number of particles in a certain box, if you like. I mean, that's how you could visualize it. But this is more really in terms of quantum states or microstates. Yeah. Now, so that's the statement of the master's equation. This is a very generic equation. Now, how to use it to discuss, to discover more properties of our statistical mechanics systems, and that's what we are going to discuss. As I said, that the Hamiltonian can be written as H0 plus Hi. Hi is a small interaction term, and the systems are in quantumizing states of H0, and Hi causes transitions between R and S, and vice versa, S and R. Now, for a isolated system, it can be shown if Hi is Hermitian, uh, then and it's an isolated system. So, if you're talking about microstates or equivalently quantum states, uh, the system going from R to S, where the energy of the when the energy of R and S are different, WR is equal to 0. Because if you're thinking classically, then basically the energy has to be conserved. I mean, you cannot go, if it's an isolated ground, go access any state where the energy of that state is different, right? If it's isolated. But but uh, but there can be transitions if Hi is Hermitian, then there can be transitions between R and S if energy of R and energy of S is the same, and it can be shown because Hi has to be Hermitian then that WRS, that is the transition probability from going from R to S and S to R, has to be then equal, right? And it can be seen from quantum mechanics. So if energy is the same, then the transition probability from R to S and S to R has to be equal, because because the transition probability can be written as like bra Hi R kit R a whole square, and I mean, basically you have this relationship. It's from there that it comes. But for transition between different states with different energies, Hi necessarily has to be non-Hermitian, and only then you can go from one state to the other where the energy of the two states are not the same, right? This will be taught during transition probability in some quantum mechanics too, or something like that. Now, with this background knowledge that WRS equal to WSR, right? With this background knowledge, if energy is not changing, because then Hi has to be Hermitian, uh, then then one can use that knowledge of transition probabilities, that WSR has to be equal to WRS in this equation, right? In this so-called master's equation. Now, remember that previously we had demanded that all microstates have to be equally probable, that the probability of occupation of any microstate has to be equal. So all the PRs, all P has to be equal to PR has to be equal to PS. Right, so that's what we had assumed in the past, but now we can see that if all these have to be equal, and then in equilibrium dpr dt, also is not evolving because it's in equilibrium. It's not time varying anymore, right? It has reached equilibrium. It continues to be in equilibrium. Entropy is maximized. It's isolated system, so there's no reason that once it has reached equilibrium, it is going to evolve in some way. There's going to be some current induced, right? If it was non-equilibrium, it will reach equilibrium, and we shall show that. But once it's in equilibrium, all microstates are equally probable, and dpr dt has to be equal to 0, and then uh, one can argue that independent of whether a system is in equilibrium or non-equilibrium, uh, suppose there is a Hamiltonian and there's a particular quantum state or equivalently microstate, right? So locally, the system doesn't know whether the system is in equilibrium or not. So the transition probability itself is going to depend upon the energy of interaction, right? So the transition probability is not going to change whether the system is in equilibrium or non-equilibrium, because uh, it's a local property, right? Or well, if it's so that's a property of the Hamiltonian, and whether the system is in equilibrium or not is the property of these large number of particles, right? So WSR equal to WRS, if energy is not changing, it will it is unchanged whether the system is in equilibrium and non-equilibrium. However, if a system is in non-equilibrium, then the probability of being in different microstates or different in quantum states will be different, right? And suppose PS and PR was so suppose PR and PS were not equal, that is, the system was not in equilibrium, then there will be corresponding, so since WSR equal to WRS, there will be corresponding changes in dpr dt till they become all equal. Now how does one show that? I think I'm showing that in the next line. So before we go and give the arguments, let me tell you the primary result. So that is, if a system is in equilibrium, all the probabilities are equal and they're not changing, right? So basically dpr dt equal to 0, and all the WSR equal to WRS, and all the probabilities of all the quantum states or the microstates are the same. So each of these terms within the summation has to be individually equal to 0, and that's equilibrium. However, dpr dt could be non-zero. Dpr dt could be 0 when the individual terms under the summation have a finite value. Then each of them are non-zero, but the sum of all these terms are equal to 0, and then the system is in steady state. There's a net current from one microstate to the other because each of the individual terms are non-zero. There are some net transfer of probability, I mean, from a particular pair of states, but all over sum of S equal to 0. So that will be the steady state, whereas if each of these terms are individually 0, that's the condition of equilibrium. That's no current from one microstate to the other, net probability current from one microstate to the other, right? So if by chance different microstates had different probability, right? Now since WRS equal to WSR, that would give that would give a net current, probability current, such that the probability of R would, suppose PR is greater than PS, suppose, right? Then there would be a net flow of probability. Now, the flow of probability means there will be a net movement of systems uh, from R to S, so that the number of number of systems in state S increases, right? And it will go on till all the probabilities become equal, and then it will become consistent with the initial assumption or postulate of equal a priori probability. So how does one see that? Now suppose in isolated systems, dpr dt, let's write that as sum over S, WRS equal to WSR, and PS minus PR. So if PS was greater than PR, right? So then this would be a positive quantity, right? So PS minus PR would be a positive quantity, and dpr dt, rate of change of PR with T, would change, the slope would be positive. And correspondingly, if we wrote down dps dt, that would be WRS into PR minus PS, and that would be a negative quantity. So the probability of S, or equivalent to the number of systems which are in state S, that would decrease. The number of, and the probability of being in state R would increase. They would keep on changing till what time? Till all the PRs and PSs become equal, and then each of these terms will be individually equal to 0, right? So that's the condition for equilibrium.